Hello everybody and welcome to the final video on functions. In this video I wrap up the entire topic doing two things. I will show you an example of how functions can streamline your code, and I will introduce the topic of recursion. So the example I won't take very long with. I want to just recall the example of the game of Nim, which we talked about maybe 2 weeks ago or something. So here's the game of code that we looked at originally. So remember that Nim is this game where you have a bunch of piles of stones, and on your turn you choose a pile and then you remove a certain number of stones from that pile, and the person who takes the last overall stone wins. So here's the code that we looked at before. This is the code that's on Moodle now, so you can bring this up and look at it yourself if you want to. But notice there are no functions here. So, here's where I play the game, choose a pile, how many rocks do you want? I then make sure that that what they gave me was legitimate. If there are only 5 piles, I can't choose pile 8. If a pile only has 3 rocks in it, I can't choose 7 rocks, things like this. And then I update the number of stones, I update the number of total stones, I update the number of stones in the given pile, etc. And then the computer takes a turn. The computer randomly chooses a pile. I then make sure that the pile that the computer chooses is non-empty so that the computer can take a stone, etc. So I don't want to walk through everything here, but that's the basic setup. So, it's just what we looked at before. Now, let me put in the same program. This will do the same thing, but with functions doing a lot of stuff. So this code is also on Moodle, so feel free to follow along with that code on your own, and feel free to play with that code. But let's just go to main now. Here is what main looks like in this code I've set up using functions. And so in the interest of time, I don't want to walk through everything. You have the code there yourself, so you can see what's happening. But notice that I've rewritten main to look a lot like English. So I start by declaring my piles vector. I then wrote a program that initializes that. So initialize the game board, please, is what this says. And if you go down to the initialize game board function, here it is. What it does is it's outsourced that getting of the pile sizes from the user. So initializing game board, that function itself does the question. How many piles are in a or how many rocks are in a given pile? And then you actually set the pile size to what you want. And there's also a little validation check loop inside of here that forces the user to give you positive numbers, or at least not 0 numbers anyway. Okay, so back up in main, if another programmer comes along and looks at this, they know what's happening here. Oh yeah, so he's writing this game program. He's going to start by just building the initial configuration of the board, and then I say, okay, here's the start, and then I display that board to you. So what does the function display game board look like? Let me just come down. Display game board, I simply give it a vector and I have it print that vector. So back up here, when I say display game board and then I hand it this piles vector, that piles vector is just the initial list of pile sizes. So I'm just handing this function the game board and asking it to show you the game board. I also wrote a function that calculates the number of total stones. And so to do that, you need the total stones variable itself, and you need the game board so that you can go through and add. And so down here, where is this? Calculate total number of stones. Notice I pass number of stones by reference so that when I actually calculate the total number of stones, that calculation is remembered back in main. So that back up here in main, where was it? Calculate total. So total stones, right? Initially it's 0. I pass it by reference so that the calculation of the total down below is remembered. And then we go into gameplay, choose a pile, how many rocks? I then check that this number is valid, so I've outsourced that validation stuff to a function. I then update the game board and the total stone count. So the user just made a choice, right? They chose a pile. They removed a certain number of rocks from that pile. I then update the game board based on this choice they made. And once I've updated the board, I then display it back to them. If there are no stones left, the user won. Now we move on to the computer's turn. So the computer chooses a pile. The first thing I do is make sure the computer chose a non-empty pile. Okay, then the computer chooses a certain number of rocks to remove from that. Once the computer has made these two choices, a choice of a pile and a choice of a number of rocks to remove, I then update the game board again, just as I did after the human user made those choices. After the computer's turn, I then display the game board. And if the computer took the last rock, you lost. Okay, so again, you perhaps don't have the same aesthetic sense as I do, but this is way nicer to read, in my opinion, this main, where it's just you've outsourced codes and you've used descriptive English to say what that outsourcing is doing. So like, oh, check that the number is valid. I know what that's doing. Update the game board and update the total stone count. Okay, I see what that function is doing just from the English name. So this main here, so main starts right back up here. This main is far more streamlined and far more readable to another programmer than the original code that I had up here. That original code had no functions, right? But now you can just come along and read this like it's bedtime reading or something. You know, just, oh, he initializes, he shows the game board to the screen, he calculates some stuff, he does some sort of validation check thing, he then updates the board based on what the user just did, etc. Okay, so anyway, this is on Moodle. You can take a look at it if you want to. The reason I'm showing this to you is that I hope you now see how functions can be useful. And again, imagine this was a much bigger game. You would just have far more of this English in here. You'd have far more tasks outsourced down below so that another programmer can come along and say, update game board and total stone count. I wonder how he did that. They can jump down here to update game board and total stone count and see what happened. Oh, so he gave the function the game board, he gave the function a choice of pile, he gave the function the total stone count, and he gave the function the number of stones to remove. And then he simply updates the size of the pile, and he updates the total number of stones. And since I passed the piles vector and the total stones variable by reference, these changes down here are remembered back up in main. So take a look at this yourself. Hopefully you see how nice it is to streamline things. Hopefully you also see the power of passing by reference. So notice I'm passing by reference all over the place. And I do that, like in this case here. This case I'm doing it just to save memory. Okay, so as I've told you before, sometimes programmers will pass by reference simply to avoid making copies of things. So here I've avoided making a copy of the game board. I simply pass the game board itself and then you print. Other times I've passed by reference to actually change things. Okay, so again, that's on Moodle. Feel free to play around with it, see if you can understand what those functions are doing. We don't have time in this video to go through everything. So let me now clear all of this out so that we can move on to recursion. Here we go. Okay, so a blank slate for when we come back. Okay, so look at an example of how functions can streamline code. We just did that. Now let's move on to recursion. To motivate the idea of recursion, I want you to consider the following paradox. So statement 1 here is that living things are machines. Statement 2 is that living things can self-reproduce. Statement 3 is that machines cannot self-reproduce. So this is a system of 3 statements. 2 of them are about living things, biological things, I guess you would say, and 1 statement is about machines. And so I'd like you to think about whether or not you agree with these 3 statements. So certainly you agree with statement 2. Living things can indeed self-reproduce. Think about an amoeba splitting into 2 or whatever, you know. Think about this statement, machines can't self-reproduce. That seems sort of self-evidently obvious, I suppose. I'll make an argument for this in a second, but it seems kind of obvious that that is true. And statement 1, you may or may not agree with that because the word machine is kind of has negative connotations or something, but this statement 1 is sort of a tenet of modern biology. Okay, so once we've understood these 3 statements, I just want to briefly argue for why these things are true. Yeah, so the paradox, of course, if you accept all 3 of these statements, what is this saying? Living things can self-reproduce. Oh, but living things are machines, and machines can't self-reproduce. So the paradox here is that living things can both self-reproduce, but also can't. So all 3 statements seem to be true, and yet if you accept all of them, you contradict yourself almost immediately, right? Living things reproduce. Oh, but living things are machines, and machines don't reproduce, Okay, so I briefly want to argue for why these things are true. At least number 3. Because as I say, statements 1 and 2 are the least controversial. To me, statement 2 is obviously true. Statement 1 is more or less a tenet of modern biology, that you can sort of understand living things from some sort of deterministic, machinistic, whatever perspective. So let's think about statement 3 there. I want to argue that machines can't reproduce. So consider a machine that constructs other machines, like an automated factory that produces cars. The factory itself must be more complex than the car that it's building, because the factory contains the car's designs within it. Okay, so if a machine is going to build another machine, the building machine needs to be more complex than the machine that is built. That's what I'm saying. So if A is a machine that produces machine B, A must be more complex than B because A sort of contains B within it. Therefore, A couldn't produce itself because A can't be more complex than itself. So here's an argument for statement 3, that machines can't self-reproduce. If you had a machine that self-reproduced, that machine would be more complex than itself, and clearly that's not true. Okay, so actually, that argument I just gave you has a hole in it. I will leave it to you to think about what's wrong with this. It certainly looks convincing to me, at least, but actually this argument doesn't hold water, and item 3 actually is false. Machines actually can self-reproduce. So what seemed like a paradox actually is not. So living things can self-reproduce. Even if living things are machines, we won't contradict ourselves because machines can self-reproduce. The idea of machine self-reproduction is called recursion. So to give you a concrete example of this, I'm going to talk about recursive functions because we are in the functions section of material here. So what I'm going to show you is sort of an example of recursion in action. But the idea is basically this function can reproduce itself. So a recursive function is a function that has itself within it. Okay, so back up here I said, you can't have a machine produce itself because you can't have the machine's designs within itself or something, But recursive functions actually have themselves as part of their design. So they're pretty cute if you think about it. So I'm going to build this example for you that will compute the Fibonacci numbers, or at the very least will compute the nth Fibonacci number. But the thing to keep in mind before I write this example is that we have seen examples of functions calling on other functions. So for example, back here in the compiler, main, that's a function itself. It's the main function. And that function calls on other functions. It called on, whatever it was, update, game board, right? Whatever, like it called on that function. And we've seen examples in previous videos where we had a function down here that was like a bool, search kind of guy, whatever, and that function called on another search function, namely the int our string find function. We saw an example like that. So functions can call on other functions if you want them to. So since functions can call on other functions, they can actually call on themselves. So what I'm going to do here is build a recursive function that calls on itself in order to help build the sequence of Fibonacci numbers. Okay, so let's actually do it. That's all sort of abstract. Let me actually show you how this works. First of all, here are the Fibonacci numbers, 0, 1, 1, 2, 3, 5, 8, etc. If you haven't seen these before, you may pick up on a pattern pretty quickly here. Notice that this number here is the sum of the previous two numbers. This number 2 here is the sum of the previous two numbers. 3 is the sum of the previous two numbers, right? 8 is the sum of the previous two, etc. So that is how this sequence is built. The nth entry in the sequence, so the nth Fibonacci number, is the guy right behind it plus the guy 2 spots behind it. So the nth guy is the sum of the previous two guys. So let's write a function that takes an integer n and returns the nth Fibonacci number. So if I input the number 4, the function should give me 2 back because 2, as you can see, is the 4th Fibonacci number. If I input 8, the function should return 13 because 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 13 is the 8th number, and so on. And I guess I should point out that since we are building this function ourselves, we can start counting at 0. So we can call this position 1, position 2, position 3, etc. We can count like we normally would. So C++, of course, would call this the 0th number, the first number, second number, third, etc. But since we're in control now, we will just start counting like we normally would. Okay, so what does this function look like? Well, at the very least, it's giving me an integer back, right? If I give it 4, it gives me the Fibonacci number at position 4, right? So it's going to give me an integer back. Let me just call it Fibonacci. What I have to hand the function is the nth position. So I have to tell it which number I care about. Do you want the first number, the 7th number? You know, whatever. You have to tell it that. So as it says here on the slide, you want to input a position inside that sequence and give back the number at that position. Okay, so now let's actually build the function. So in order to get the recursion going, notice that this statement here, that the nth number, let me zoom back in on this, the nth number equals the sum of the previous two. Notice that only makes sense starting at this one on. Okay, that statement only makes sense for numbers that have 2 previous entries, right? So this number 0 doesn't have any previous entries at all. This number 1 only has 1 previous entry. It doesn't have 2 previous entries. So the first time in the sequence where this statement makes sense, like, hey, take the previous 2 guys and add them. The first time that makes sense is right here. So what that suggests is if we want to build this rule, we can't build it for these first 2 guys. But that's okay. So the first 2 guys, I'm just going to hard code in. So if n equals 1, what the user wants is the first Fibonacci number. So let's just give that number back. So if n is 1, what I'm asking for is the first number in the sequence. That first number is 0. So I'm just giving that right back. Else, if n is 2, what the user is asking for now is the second number in the sequence. Well, the second number is 1. So back up here in main, I'm not sure if it'll let me do this because of that red down there. That red, again, it's worried that I'm supposed to return an integer, and it's possible that neither of these branches run, right? So if n is 7, the thing won't know what to do. That's what it's worried about. So let's just see if it'll do fib1. Yeah, it won't let me do it. But once we finish building the function, if you input 1, it will output a 0. So it will show you what's on the screen. So again, the reason this red is here is because this if-else-if structure here, you don't have to run either of those. So if I enter a 3 right here for n, it won't know what to do. So it's worried about that. So let's just go ahead and build the function. Okay, so suppose I enter the number 3 or the number 4 or the number 18, whatever. What is the function supposed to give back to me? Well, it says it right here. If I enter n, the Fibonacci number at position n is the n minus first Fibonacci number plus the n minus second Fibonacci number. Okay, so let's just write that. If I get something bigger than 2, let me just give you back the Fibonacci number of 1 to the left and the Fibonacci number 2 to the left. Okay, so what's this saying? This is saying if I enter the number 1, give me a 0 back, please. That creates 0 as the first number. If I enter a 2, give me a 1 back, please. And that will put 1 as the second number. If I give you any other number, what I want you to do is take the sum of the previous 2 Fibonacci numbers and give that back to me. So before we play with this in the compiler, I just want to point out a few things. First of all, notice that this function is feeding on itself, right? So the function is called fib, and it calls on itself inside of itself. So on some level, this function contains its own design inside of itself, right? So this function is sort of like a self-producing machine. This is, because functions are machines. They are abstract machines. I have built a function that sort of feeds on itself to produce itself. So that's pretty neat. Also, before playing with it, I just want to actually talk through what the function's actually doing. So how does this function know what fib of 5 is? Okay, what's actually happening here? Since 5 isn't 1 or 2, so let me just keep these things parallel here. Okay, so notice if it were fib of 1 or fib of 2, the function knows exactly what to give back to you. It either gives you back a 0 or a 1. But 5 is not 1 or 2. So the function is going to return fib of 5 minus 1 plus fib of 5 minus 2. So the function gives back this sum. But that, of course, just begs a question, well, what's fib of 4? How does the function know what that is? What's fib of 3? How does the function know what that is? So let's start with fib of 3. 3 isn't 1 or 2. Because if 3 were 1, you would go in here. If the number were 2, you'd go in here. But 3 isn't 1 or 2, therefore I go in this branch, and the function returns fib of 3 minus 1 plus fib of 3 minus 2. So the function gives back the first Fibonacci number plus the second one. But the function knows what those are, right? The function knows what fib of 1 and fib of 2 are because I've hard-coded those in. Fib of 1 is 0, fib of 2 is 1. So the function knows that fib of 3 is the sum of those things, which gives you 1. Okay, well, how does the function know what fib of 4 is? Well, fib of 4 is, again, 4 is not 1 or 2, so I go into this branch down here. Fib of 4 is fib of 3 plus fib of 2. Oh, okay, but I know what fib of 2 is because I've hard-coded that in, and I know what fib of 3 is because I just calculated it, right? So the function knows from the get-go fib of 2 is 1, and the function also knows that fib of 3 is 1 because of, fib of 3 is just fib of 1 plus fib of 2, as we just did. Therefore, the function knows that fib of 4 is 2. It's 1 plus 1. Okay, well, if the function knows what fib of 3 and fib of 4 are, then the function knows what fib of 5 is. It's just the sum of those two guys, and it'll give you a 3. So here in the compiler, let's just ask it, what do you think fib of 5 is? And it says 3. So it knew what to do. So basically, anytime you hand this function a number like 5, what happens is a chain reaction is set off. The function initially is like, I don't know what the output of 5 is. Oh, but you've told me the output for 5 is the output of 4 plus the output of 3. Oh, but I don't know what those outputs are. I don't know what fib of 4 or fib of 3 are. But fib of 3 I know is fib of 2 plus fib of 1, and oh, I know what those are. And fib of 4 is fib of 3 plus fib of 2, and oh, now I know what those are. Oh, so now I know what fib of 5 is. So these recursive functions sort of set off a chain reaction where if I give it now, let's give it something a lot bigger, 17. So the 17th Fibonacci number. What's going to happen is 17 is not 1 or 2, so I'm going to return the 16th plus the 15th Fibonacci numbers. But the function is like, I don't know what those are. Oh, but I know the 15th one is the 14th plus the 13th. But I don't know what those are. But I know the 13th is the 11th plus the 12th. You see, so it just sort of like bootstraps its way back down to the base of all of this process. And the base of this process is that you start with 0 and the next one is 1. So therefore, you can ratchet yourself all the way back up to 17. So let's just see what the 17th Fibonacci number is. 987. Okay, we'll take its word for it. Let's do something we can actually verify maybe. The 8th Fibonacci number is 13, and that is correct, right? 1, 2, 3, 4, yeah. And the next one is supposed to be 21, and it is. Okay, so the idea of a recursive function is simply any function that calls on itself in this fashion. So this sequence of numbers, the technical language you would use is that this is a recursively built sequence. If you want to know what the nth guy in the sequence is, you have to know things about previous guys in the sequence. So you have sort of like a baseline start level, and then you move on. You take the third guy. The third guy's value depends on the values of the first two guys. The fourth guy's value depends on the value of the first and second guys, second and third guys, etc. Okay, so that's the idea of a recursive function. So if you wanted to build other kinds of functions, like, suppose you wanted to build a sequence where we start with 0 and 1, but we don't take the sum of the previous two guys, we take the difference of the previous two guys. I don't know. Then you would change your function like that. You take the difference of the previous two guys. So now, the ninth guy in that sequence would be 1, I suppose. Okay, so at the end of this video, hopefully now you like functions a lot because you saw how readable nim became when I used those functions. And again, that's on Moodle. I will also place this little toy example on Moodle of Fibonacci numbers. But hopefully you are now at least somewhat comfortable with the idea of a function calling on itself, which means the function is recursive. And hopefully you have some idea of the sort of chain reaction that's set off when you ask the computer what fib of 9 is. Right? So initially the computer doesn't know, but it does know what fib of 1 and fib of 2 are, and so therefore it can figure out what fib of 3 is, therefore fib of 4, fib of 5, all the way up to fib of 9. And again, philosophically, these functions are quite interesting because philosophically, these functions are on some level counterexamples to this statement. These are abstract machines that contain themselves within themselves. Okay, so really, really cute functions. Okay, that's it.